All right, let's jump right into this. Welcome to this explainer, where we're going to uncover the absolute genius engineering that keeps modern jet engines from just completely failing when they fly through torrential, storm-level rain. I mean, we've all been there, right? You look out the airplane window during a massive thunderstorm, and you just kind of wonder, how on earth do those engines keep running while seemingly swallowing an entire ocean of water? Well, today, we're going to break down exactly why modern jets don't explode when they suck in heavy rain, and it all comes down to some incredible aerothermodynamics and structural mechanics.
To really wrap our heads around the scale of this threat, just consider this number for a second. 4 tons. 4 tons! During a severe storm, a single high-bypass turbofan engine can swallow over 4 tons of liquid water and solid hail every single minute. That is a staggering amount of mass to dump into a highly complex, rapidly spinning machine that, by the way, is simultaneously burning fuel at over 1,500 degrees Celsius.
Section 1. The heavy rain threat and its underlying paradox.
So, this massive intake of water brings us to a really fascinating paradox. Basically, everything our intuition tells us about everyday engines says they should be instantly destroyed by that much liquid. Think about your everyday car engine. It's a closed-cycle reciprocating system. If you suck a big puddle of water into your car's air intake, the piston tries to compress it, but water is essentially incompressible. The result? A catastrophic hydraulic lock that literally bends rods and shatters the engine. It's game over. But a jet engine? Completely different story. It operates on what's called the open-cycle Brayton thermodynamic diagram. Basically, it's just a giant open tube. Because it's completely open at both ends, there's no physical containment chamber to trap the liquid. Any water that doesn't evaporate just passes straight through the machinery, completely avoiding that deadly mechanical lockup.
Section 2. First defense. The great aerodynamic spin.
So, knowing the engine won't literally shatter, how does it actually handle all that water? Well, the journey starts at the very front of the engine, which acts as our first major line of defense. Think of it as a massive active aerodynamic separator. The millisecond water hits the engine, physics takes over. Those rapidly rotating fan blades act exactly like a giant centrifuge. Because water is about 800 times denser than air, it has way more inertia. So the fan imparts this massive outward velocity to the water. The heavy water droplets inhale, they just can't make the rapid aerodynamic turns required to get into the core airflow. Instead, the centrifugal force aggressively flings them harmlessly outward, bypassing the sensitive engine core entirely. In fact, up to 90% of the water just flows straight out the back of the bypass duct.
Now, this centrifugation process wasn't always so perfect. Early engine designs used these simple cone-shaped spinners right in the center of the fan. The problem was, ice and water would hit them and bounce straight back into the core, which was really bad news, especially at lower speeds. The engineering fix for this? The modern caniptical spinner. It's this brilliant hybrid shape, a pointed tip with a curved elliptical base. It actually harnesses combined Coriolis and centripetal accelerations. So instead of bouncing off, the water and ice slide smoothly along that curve and get violently flung outward into the bypass duct. It completely solves that dangerous bounce-back effect.
Section 3. Second defense. Flushing out the core.
Okay, but despite the fan doing all that heavy lifting, a highly atomized fraction of water, basically a superfine mist, will still slip through the inner blades and get into the engine's core. And that brings us to the second line of defense, passive mechanical extraction. Right after the initial booster stage, the air has to navigate through what are called S-ducts. These are just curved transition sections leading to the high-pressure compressor. Remember how we said water is 800 times denser than air? Well, that huge momentum comes into play again here. When the S-duct forces a really sharp turn, the air makes the corner just fine, but the heavier water droplets simply can't. They essentially skid to the outside of the turn and smash into the outer casing wall. This gathers all that scattered mist into a concentrated film of liquid water that just slides safely along the outer engine wall, keeping it far away from the delicate compressor blades.
But obviously, we can't just leave a river of water sliding along the inside wall of the engine forever, right? Enter the variable bleed valves, or VVVs. These are essentially trapdoors built right into the wall of that transition duct. Acting like a super smart high-speed drain, these doors pop open during heavy precipitation. They bleed off a bit of the compressed air, and because our liquid water is conveniently pooled right up against that outer wall, the rushing bleed air sweeps that entire film of water completely out of the core and dumps it right back into the bypass duct.
Section 4. Third defense. Evaporation and power boost.
So we've centrifuged the bulk of the water away, and we've bled out the water along the walls. But what about the really microscopic stubborn mist that finally makes it deep into the high-pressure compressor? Well, here we get a brilliant little thermodynamic magic trick. You know, a lot of folks assume that freezing rain hitting red-hot metal turbine blades would just shatter them through thermal shock. But the crazy thing is the liquid water never actually touches the hot metal. As the air is compressed inside the engine, it heats up incredibly fast, often hitting over 500 degrees Celsius just from the pressure alone. So the water droplets absorb that heat and flash into superheated steam before they ever reach the metal. And get this, it takes only about 1% of the engine core's total thermodynamic power to fully vaporize all that ingested water. It's literally just a drop in the bucket for the engine's overall energy output.
And here's where it gets really wild. Counterintuitively, sucking in a bunch of rain actually gives the engine a power boost. I know, it sounds fake, but it's true. First, there's evaporative cooling. As that water flashes to steam, it pulls heat from the surrounding air. This cools the compressor, making the air denser, which means it can pump even more mass into the combustor. Second, we have mass flow augmentation. When that liquid water turns to steam, it expands by over 1,600 times in volume. That adds a massive amount of non-combustible mass to the exhaust stream. And in jet propulsion, pushing a heavier total mass out the back nozzle literally equals more thrust. Fun fact, older jet engines used to actually deliberately inject water into the compressor during takeoff just to harness this exact thermodynamic boost.
Section 5. The digital brain.
Now, tying this entire physical fortress together is the engine's full authority digital engine control, commonly called the FADEC. All that fancy physical separation we just talked about means absolutely nothing if the combustion flame gets snuffed out by a sudden wave of water. The FADEC is the digital brain actively overseeing the whole operation. It's constantly monitoring everything: spool deceleration rates, internal pressure ratios, you name it. If it detects the unique aerodynamic signatures of water entering the engine, like a sudden temperature drop or pressure weirdness, it instantly executes a rapid, automated defense sequence. Most importantly, it triggers continuous, high-energy sparks in the combustor. Normally, jet igniters turn off once the engine is started, but in a storm, the FADEC forces them back on, continuously sparking. That way, if a huge gulp of water transiently snuffs the flame, the continuous spark immediately relights it before the engine even has a chance to spool down. It's pretty amazing.
The FADEC also tackles a really dangerous phenomenon called the scoop factor. Basically, at low engine power and high flight speeds, like when a plane is coasting down for a landing, the engine isn't demanding a lot of air. So excess air just spills harmlessly around the front lip. But heavy rain and hail, they have too much momentum to spill away. They get scooped right into the inlet. This drastically spikes the water-to-air ratio inside the engine. To counter this digitally, the FADEC automatically bumps up the minimum idle speed. By forcing the engine to run just a little bit faster, it draws in way more air to dilute the water, and crucially, it spins the fan faster to guarantee it has enough centrifugal force to fling that water away.
So the big takeaway here is that a jet engine in a rainstorm is absolutely not fighting for its life. It's functioning exactly as it was mathematically designed to. Between the open-cycle Brayton design preventing hydraulic lock, the active aerodynamic centrifugation spinning the water away, the mechanical S-ducts draining the boundary layers, and the FADEC actively managing the combustion, you can totally sit back in your seat and relax. You're not looking at a fragile piece of machinery out on that wing. You are looking at a literal thermodynamic fortress that just effortlessly conquers the storm. But, you know, if engineers have so thoroughly mastered something as chaotic as a severe thunderstorm, it really makes you wonder, what other incredible invisible safety systems are quietly working to protect you up at 30,000 feet? Thanks so much for joining me on this explainer.